Welcome to this presentation. I am Sharik Kasira from Rajasthan chapter. Today, we South Africa chapter and Rajasthan chapter are jointly celebrating the World's Refrigeration Day with a virtual distinguished lecture presentation on Introduction to the Ammonia Refrigeration System. I welcome Dr. Douglas Hindle, ASHRAE Distinguished Lecturer. I would also like to welcome Mr. Richard, President, ASHRAE South Africa Chapter, and Mr. Rishabh Kasliwal, President, ASHRAE Rajasthan Chapter. So, World's Refrigeration Day is celebrated annually on June 26. The day was chosen to celebrate the birth date of Lord Kelvin on 26 June 1824. It was created to raise awareness about the importance of refrigeration technologies in everyday life and to raise the profile of the refrigeration, air conditioning, and heat pump sector. The World Refrigeration Day was the idea of refrigeration consultant Stephen Gill, former president of the Institute of Refrigeration in the UK. In October 2018, ASHRAE pledged support for World Refrigeration Day. In January 2019, ASHRAE awarded Gill its John F. James International Award in Atlanta. In February 2019, the United Nations Environment Programme pledged support at the UNEP National Ozone Officers Meeting in Paris. The inaugural World Refrigeration Day was held on 26th of June 2019. So it was the history of the World Refrigeration Day. Now I would like to request Mr. Rishabh Kasliwal to introduce our guest and today's session. Over to you, Rishabhji.
Thank you, Shailendra. Welcome, friends. Very exciting day for all of us, World Refrigeration Day. Thanks for the introduction. On behalf of both the ASHRAE Rajasthan chapter as well as ASHRAE South Africa chapter, a big welcome to our guest, Professor Douglas Hindle. I'll be referring to him as Doug at his request. So here is I have a very nice introduction, some words about him for all our members here. So Professor Hindle is a professor and chair with appointments in the Department of Engineering, Professional Development, and Mechanical Engineering at the University of Wisconsin-Madison, popularly known as WISMAD. In addition, he is the founding director of the Industrial Refrigeration Consortium at WISMAD. He received his BS in Mechanical Engineering Technology from the Milwaukee School of Engineering and his MS and PhD degrees from University of Wisconsin. He's a registered PE in the state of Wisconsin and actively involved in ASHRAE, IIAR, and IIR. A lot of refrigeration background there. Perfect for today. As a faculty member at the university since 1996, Doug has taught at all levels, undergrad, graduate, and continuing professional development. We were just incidentally talking about that a few minutes ago. He has developed an internationally recognized series of professional development courses which focus on industrial refrigeration with an emphasis on the safe use of ammonia as a refrigerant. Through the IRC, he collaborates with the world's leading food companies to improve the safety, efficiency, reliability, and productivity of these systems and technologies. Just on the previous slide, Shailendra was showing us about the cold chain piece also. And as we all know, it's a big and developing thing, especially in our part of the world. Professor Hindle is an ASHRAE Fellow and a past president of ASHRAE's Distinguished Service Award. He was the first recipient ever of ASHRAE's George C. Briley Award for the best refrigeration article in the journal. He's a past chair and currently serves as a member of ASHRAE's Standard 15 committee, which, as you know, is the safety standard on refrigeration. He has published 7 books and over 100 technical papers. Just FYI, if you go on Google and type his name, you will see that he has over 3,000 citations, and not just in refrigeration, but in many other topics. And he's an expert on not just refrigeration, but solar energy and industrial systems as well. So we are honored to have him amongst us today. And I have many more lines here, but in the interest of time, I'm going to stop here introducing our guests and move on. Next slide, please. Before I hand over to our guest or back to Shailendra, just a quick introduction for our listeners. Uh, Industrial refrigeration systems have used anhydrous ammonia for more than a sesquicentennial. Although ammonia has a long history of use in the industrial sector, the interest in ammonia as a potential refrigerant has grown recently. This presentation provides an overview of these systems as they are very important in the industrial sector and they have some unique characteristics. So with that, once again, welcome, and I hand over to Shailendra.
Thanks, Rishabhjeet. Nice introduction of our guest in today's webinar. I would like to read the ASHRAE Code of Ethics. In this and all other ASHRAE meetings, we will act with honesty, fairness, courtesy, competentness, inclusiveness, and respect for others, which exemplify our core values of excellence, commitment, integrity, collaboration, voluntarism, and diversity, and shall avoid all real or perceived conflict of interest. So before handing over to Professor Doug, I request all the participants to raise the query through question and answer tab only. The professor will answer your questions after the presentation. A recorded version of this webinar will be available at the YouTube channel of ASHRAE Rajasthan chapter. Now I request Professor Doug to deliver the webinar on introduction to the ammonia refrigeration cycle. So I'm sharing the screen.
It's great to be
So,
with you.
Professor
Thank you
Doug.
for that kind introduction. It's really fitting today on World Refrigeration Day, with the theme this year being the cold chain, to talk about ammonia refrigeration systems, because this technology and also the refrigerant has really been the backbone of the cold chain from its beginning. So this is a great topic. Thanks for having me with you this evening. So I'd like to start out by just talking a bit about ammonia and some of its uses, and you'll see in just a moment that as a refrigerant, it's a very small percentage of the use of this chemical. But then I want to focus in on anhydrous ammonia as a refrigerant, some of its properties, some of its attributes, and how it's different than other refrigerants that maybe you're more familiar with. And then I want to go into a bit more detail on the technology to give you a sense for how these systems are put together, how they're configured, what the equipment looks like, and how the systems actually work. I'll focus on single stage compression systems. Those are the easiest and most approachable to understand at sort of a basic level. And we'll look at the three most common configurations for evaporators on these systems, what we call direct expansion, gravity flooded, and liquid overfed. And then depending on how we're doing on time, I'll maybe introduce what we call two-stage or compound refrigeration systems. Last year, globally, we produced 150 million metric tons of anhydrous ammonia. And as you can see, the lion's share of use of ammonia is as a fertilizer, a nitrogen source for crop production. So almost 90% of the consumption of ammonia is as a fertilizer. Only a very small sliver of the global production is dedicated for use as a refrigerant. It's on the order of about 2%. The four largest producers of ammonia last year I've sort of listed at the top, with China leading the production at just about 27%, Russia, the US, and India kind of clustered around 10% of the global production. And listed on this slide is some of the other names that are used to describe ammonia. ASHRAE standard 34 has a refrigerant designation, which is unique for each refrigerant. The refrigerant designation for ammonia is R717, and you'll hear it referred to as spirit of hartshorn or azine or ammoniac. Those are some of the other names that we refer to ammonia as. These systems use what's called anhydrous ammonia, And anhydrous is simply a word that means without water. So by and large, the ammonia that's used in these systems has a very low concentration of water. And as a refrigerant, this has been the mainstay for industrial systems, as it was noted before, for 150 years. So it's typically used in large food processing facilities and also large distribution warehouses. It is finding some use and has found some use in HVAC systems, primarily in chillers, because for air conditioning applications, we can't use ammonia directly. We have to have a secondary fluid. And I'll show you one example of a pretty prominent facility that some of you have probably been in, but you may not know that the central plant for the air conditioning system in that facility is actually an ammonia refrigeration system. And the interest is, as we search for, the fourth generation of refrigerants as the phase out of HCFC 22 occurred in January this year, and the continued search is on for obviously refrigerants that have no ozone depletion potential, but now the push to find refrigerants that have low global warming potential. Well, ammonia gets pretty interesting because it has 0 ODP and no global warming potential either. From a systems perspective, what's unique about this infrastructure is the systems are custom engineered to meet the specific needs of the process or the facility where it's going to be located. And just by virtue of the scale of this infrastructure, they're very seldom factory built. They're often built in the field for the express purpose of their application. There is now sort of a push by a number of manufacturers to package these systems so that they're easier and more accessible for a wider range of applications to be deployed in the field. But typically, the lion's share of the infrastructure that exists right now were factory built, or sorry, field directed instead of factory built. So this is the application of ammonia as a refrigerant being used to chill water for air conditioning that some of you may have been in. This is a photo of the McCormick Place in Chicago. And the heart of the cooling for that facility is 3 ammonia chillers. Each are 2,200 tons as part of a tri-generation system, which is producing electricity, heat, and cold. And chilled water is what's produced by these ammonia chillers that circulates out to cool the exhibition halls, a very large facility, 418,000 square meters. So that's maybe your little trivia bit for today, that McCormick Place utilizes anhydrous ammonia for chilling water and air conditioning of that facility. In terms of its characteristics, I had mentioned before, anhydrous means without water, and so the purity of this refrigerant is fairly high. It's 99.5% pure, and the water concentration typically ranges between 50 parts per million and 5,000 parts per million as a maximum. And that little bit of water actually is added at the point of manufacture, and that's to help inhibit metallurgical problems that can result from exceptionally dry ammonia. In a vapor state, the vapor tends to be lighter than air, so if this refrigerant is released in any large quantity in a vapor state, it tends to go up into the atmosphere. In a liquid state, it has a specific gravity of about 0.65, so compared to water, it's lighter than water. It's highly alkaline. It has a pH of 11.6. And one of the distinguishing characteristics of ammonia compared to the fluorochemical refrigerants is when it's present, you know it's there. It has an extremely pungent odor. It lets you know that it's there. And so typically in these facilities, when somebody smells ammonia, that there might be a small leak, they get taken care of very quickly. Most people don't particularly like the smell of ammonia, even though it is used as what's called smelling salts. And so, you might have seen, let's say, sports players will sniff small concentrations of ammonia that's mixed in with alcohol as a means of, I don't know, waking their brain up, I guess. It surely does that. Ammonia is also what we call highly hygroscopic. It is very soluble in water. It mixes together readily with water and binds very tightly. And so when you think about the human body, when we sort of break the human body down, we're about 2/3 water from an elemental standpoint. And so the fact that ammonia binds with water very tightly, it is aggressive to human tissue upon exposure. And so that's one of its primary concerns, and that's the risk of toxicity when people are exposed to high concentration. And if you get ammonia on the surface of your skin, it burns. And so the way that we deal with that is we irrigate the exposure with water to get free water to bind with rather than having the ammonia pull water from our body. So the good news is ammonia, we call it self-alarming. It's readily detectable. If you're in a leak around halocarbon or fluorochemical refrigerants, oftentimes you don't know it. They're simple asphyxiants by and large, and so the risks are similar with respect to the health and safety considerations. ASHRAE standard 34 designates ammonia as a flammability classification 2L. It's this slightly flammable or lower flammability classification. So here's a little snippet of the safety group classifications that ASHRAE standard 34 establishes for all refrigerants. There's two components to the safety group. There's toxicity, either lower or higher toxicity, and then flammability from no flame propagation to higher flammability. Ammonia sits right over here in the higher toxicity and lower flammability level of the classification. A number of the new HFO refrigerants that are being developed, hydrofluoroolefins, are also in this 2L classification. The difference is that they're a lower toxicity. So you will maybe be familiar with a number of the newer refrigerants that are being introduced into the market, and fluorochemical refrigerants are classed in A2L, slightly flammable. Ammonia will burn when presented with an ignition source that has sufficient energy to get the combustion going. When the concentration is in a fairly narrow range, anywhere between 15 and 16% is a lower flammability limit, and up to some range in the 25 to 28%. So if we have ammonia in this concentration range and we have an ignition source, it will ignite and it will produce what's called a deflagration. So not as energetic of a reaction as if we had a hydrocarbon refrigerant, but nonetheless one we want to prevent. If it does combust, one of the mitigating factors is the products of combustion. It really is oxides of nitrogen, depending on the temperature of the reaction, and then also water vapor will be produced in that combustion. If we combust some of the A2L refrigerants, similar flammability classification, they have much more hazardous products of combustion. And so again, another differentiating characteristic of ammonia with the fluorochemicals. So you might be familiar with materials of construction that are commonly used in air conditioning and chilling systems. They use a lot of copper, and of course that's for good heat transfer performance. And not only copper, but copper alloys such as brass. And those brass is used for either fittings or also in some cases bearing materials. We can't use those materials of construction for ammonia systems. Ammonia will attack the copper and will degrade its mechanical integrity, and then we'll eventually have a failure of that component. Zinc is a material that's used on the outside of the systems. I'll show you an example of that later, but we don't want to use that in continuous contact with ammonia. The number of non-metallics that are incompatible, it's a fairly long list, and I won't show that here, but like any refrigerant, we have to test the material of construction, the non-metallics, to make sure that there's no reaction. So what do we use in ammonia systems? Carbon steel is by and large the most common material of construction, and when properly protected from the outside, because the carbon steel will corrode when exposed to the elements, the carbon steel will last indefinitely. These systems have had carbon steel in them, and it just does not degrade. They don't get attacked on the inside of the systems. Principally, the risk from a degradation standpoint is oxidation that occurs on the outside of the piping. We can also use stainless steel and aluminum. Those are materials that a lot of plants are continuing to use. I was at a facility last week, and this is some stainless steel piping that they're utilizing up on the roof in order to minimize oxidation of the piping from the outside. A list of non-metallics is pretty long as well in terms of what is compatible. A pretty common one is PTFE that are used for sealing materials and components like valves. So I had mentioned before that this refrigerant is really kind of the lifeblood of the cold chain, particularly in food processing and food distribution facilities. But why is that? Well, if you think about when fluorochemicals were invented, it was kind of in the 1930s. Thomas Midgley was one of the founders or inventors of the early fluorochemicals, and so what was used prior to that was pretty much any substance that could be liquefied and utilized as a working fluid in vapor compression systems. And they found that ammonia is a pretty darn good refrigerant. It has high heat transfer rate capabilities. It's efficient from a thermodynamic standpoint. The cost of the refrigerant is low. And so if you think back to that pie chart that I showed you of the production of anhydrous ammonia, we benefit because of the large volume that's produced for use as a fertilizer. So the cost of this as a refrigerant is very, very low. And depending on what you compare it with, it's a very small fraction of the cost compared to some of the fluorochemicals, especially the newer HFOs. So low refrigerant cost is very important, particularly in some of these large systems where it's not uncommon for the system to have 30 or 40,000 kilograms or more of refrigerant. If you think about the cost of charging a system like that with a fluorochemical, just the refrigerant cost alone goes into the hundreds of thousands or more dollars. So pretty significant. I'd mentioned this before, ammonia has no ozone depletion, and it has what we would say low or no global warming impact. And what, some people give ammonia a GWP of 0. And what's interesting is ammonia is produced principally by reforming natural gas. And so a byproduct of the production of ammonia is the liberation of CO2. And so basically that CO2 has obviously a GWP of 1. That's the benchmark. And so ammonia kind of gets away with no GWP, because if we're going to try to assign some of the global warming potential to ammonia, how would we reconcile that with the CO2 that's produced in the process of manufacturing ammonia? So from that standpoint, it's viewed as a sustainable. I had mentioned its self-alarming characteristic, which is an advantage. So that's a bit of background on ammonia as a refrigerant. Let's take a look at the technology. How are these systems put together? How do they actually function? This is a small ammonia machinery room that utilizes some reciprocating compressors. And I'll show you some other photos of what this infrastructure actually looks like. So let's get started with what we call a single stage system. And it's built on the basic vapor compression cycle that's going to take low pressure saturated vapor into a compressor. This is an example of what a compressor would look like in one of these systems. That's a twin screw compressor. The compressor raises the pressure of that refrigerant. And what leaves is high pressure superheated vapor that's sent off to a condenser. The condenser is responsible for rejecting heat from the refrigerant to the outside environment. And as a consequence, that refrigerant will get cooled and condensed. So leaving the condenser is high pressure, saturated liquid refrigerant that is then throttled to a lower pressure through an expansion device. And the expansion device can be pretty simple. It could just be a manually adjusted hand expansion valve. And when we throttle that liquid from a high pressure to a low pressure, the contents will cool. We get this auto refrigeration effect, and we will have a mixture of vapor and liquid downstream of that expansion valve that immediately comes to the saturation temperature that corresponds with the pressure that we're holding on the downstream side of that throttling device, that expansion device. So this mixture of low temperature liquid and vapor flows into an evaporator, a heat exchanger that we'll use to absorb heat into the refrigerant. And the heat comes from the space that we're conditioning, or the process fluid that we're chilling, or the food product that we're chilling. The heat from the space or the process will cause the liquid portion of the refrigerant to boil off to a vapor state. And by the time the refrigerant makes its way through all of the circuiting in this evaporator, it will leave fully evaporated, no liquid present. And so we'll take that low pressure saturated vapor back into the compressor to get recompressed and reused. So the refrigerant circulates through this basic vapor compression cycle, and it's the working fluid that enables us to move heat from an area that we don't want it, a process fluid, a process product, a interior space that we're trying to maintain temperature controlled, and we reject the heat to the outside environment, or in some cases we can recover the heat to do some useful heating. So this simple vapor compression cycle is the foundation that is used for the larger field-directed systems. I'll use the term high side and low side occasionally as I talk about these systems. And the high side is just simply referring to the portions of the system that tend to run at higher pressure. And the low side is referring to those portions of the system that tend to run at lower pressure. So let's take a look at something that's a bit more akin to what you would see in a larger industrial ammonia refrigeration systems. This is a little bit more busy than that simple vapor compression cycle, but it's built on those same principles. So let me just sort of walk you through what's happening here. Let's start out on the low side here in this dry suction line. This is vapor only, and it's being drawn into one of three compressors that are shown that are running in parallel. In this case, I'm using multiple compressors to give me redundancy or to give me increased capacity to be able to meet refrigeration loads that are out in the plant. Those compressors will raise the pressure of that refrigerant and discharge that gas into a discharge line and sends off high pressure superheated refrigerant to one or more condensers that are responsible for ejecting heat to the outside environment. The condensers reject heat, the refrigerant is liquefied in that process, and the condensed liquid refrigerant, still at a high pressure, simply drains by gravity into a vessel that we call a high pressure receiver. This vessel is simply a reservoir that accumulates condensed liquid that then can feed that high pressure liquid out to loads that are in the plant. So these evaporators that are shown here are configured in what we call a direct expansion arrangement. And the key component here is the expansion valve, which in this case is a thermostatic expansion valve that will throttle the high pressure liquid to a lower pressure. And in the process, as we throttle from high pressure to low pressure, part of that upstream liquid is going to flash to a vapor, and the entire contents will cool to a lower temperature. And now that mixture of low temperature liquid and vapor flows through the circuiting of this evaporator, and I'll use warm air in a process space or a temperature controlled area to boil off the liquid portion of the refrigerant, and I'll get cooling on the secondary side of that heat exchanger. And by the time the refrigerant makes its way through all of the circuiting of that evaporator, not only has the liquid boiled to a vapor state, but I'll actually slightly increase the refrigerant temperature before it leaves this heat exchanger. So I'll have slightly superheated vapor leaving, and I'll take that refrigerant vapor back to the machinery room where we typically locate the compressors and other components in these systems, and I will recompress that gas and recondense it in my condensers, and the system will continue to function. Now, compared to that simple vapor compression cycle that I showed you, there's a few more components that are shown here, and those are intended to be able to enable a system to function and run 24 hours a day, 7 days a week, 365 days a year. I mean, these systems run continuously for long periods of time. And so we'll have things like this component, a suction trap. Well, I don't remember seeing that in my thermodynamics textbook. What's that all about? Well, if for some situation I get some unboiled liquid coming back from my loads out in the plant, these evaporators, that liquid would come back, and if I send liquid to these compressors, that's not going to extend their life. That's going to be a problem. So this vessel that's referred to as a suction trap is simply going to separate out any liquid refrigerant that may come back from my evaporators. The liquid being heavier than the gas will simply fall to the bottom of this vessel, and I'll have a transfer system that can periodically move this liquid to another part of the system where it could be reused. And principally what I'm doing is I'm separating liquid from vapor. The vapor goes out the top. The compressors will happily condense vapor. They will compress vapor. They will not compress liquid. So this is considered an engineered safety to ensure that the compressors do not ingest liquid refrigerant. This high pressure receiver is simply a reservoir that can accumulate and buffer liquid out to loads that are in the plant as they have either a need for cooling, or if they're satisfied, the liquid refrigerant in this vessel will simply fluctuate up and down depending on the call for liquid out in the plant. There's another component that maybe doesn't make a lot of sense. I have high pressure vapor coming into the condensers and condensed liquid coming out. This all functions, the transport of condensed liquid from the condensers into the high pressure receiver is accomplished simply by gravity. The liquid's heavier than the vapor, and the liquid just simply flows by gravity. This equalizer line is simply a means of preventing vapor binding of refrigerant in this high pressure receiver. So if you can imagine for a moment where I'm not feeding liquid out to the plant, if the level of liquid in this high pressure receiver is tending to rise, the vapor space that's in the top of this vessel is going to get compressed. And if that vapor space gets compressed, the pressure is going to go up. And now what I'll have is a situation where the pressure in this vessel is increasing above the pressure that's in these liquid lines trying to drain liquid, and I'll tend to vapor bind that vessel. This equalizer line gives a path for that vapor to be relieved so that I get free draining of liquid continuously from my condensers. So those are a couple of different features that were not shown in the simple vapor compression cycle, but those are examples of what practitioners found early on to be necessary to make this technology functional. So the high side of this system in terms of pressures with ammonia, this is to give you some example. It may run as low as 690 kPa or about 6 bar during cool weather operation, And then during warm weather operation, that pressure may go up to as high as 1241 bar, which would be a typical design condensing pressure. 1241 kPa, that's about 11 bar. The operating temperatures will depend on the type of compression technology that we're using, but it could be as low as 54 degrees C if we're using screw compressors, and it may be on the order of 110 degrees C if we're using reciprocating compressors. The low side in this arrangement, a direct expansion system, typically we'll see limited to about minus 11 C. That corresponds to about 265 kPa in terms of the corresponding pressure. Some DX systems will run lower, but this is what I would call the traditional sort of low point. And if we wanted to run a system to meet loads at lower temperature, we're going to utilize one of the other two technologies that I'll show you in a moment. And with this particular arrangement, one of the things that I can do is I can run these evaporators at different pressures using a common suction pressure that's lower. So if I had loads that had a warmer temperature requirement, I could put a regulator in order to regulate up the pressure in this evaporator, run it at a slightly higher pressure, 383 kPa, which would allow me to have the refrigerant evaporating at a warmer temperature, now minus 3 degrees C. And I may have another process need that has a higher temperature requirement that I could have connected to the same system. So I don't need to buy a separate set of compressors and, condenser, that sort of thing. Here I could run another set of evaporators that maybe have a warmer temperature requirement, maybe 5 degrees C, and I could have a regulator that regulates up the pressure to 516 kPa in order to achieve that 5 degrees C evaporating temperature. So the compressors in these systems are fairly large machines. These are two examples. The one on the left is a single screw. The one on the right is a twin screw. The actual compressor is shown here in the circle, and the single screw, that's the compressor. The dominant feature in these machines is this vessel that the compressor sits on, and that's an oil separator. The screw compressors are flooded with oil to provide sealing of the rotors, and what we want to do is keep the oil resident in the compressor, not circulating out in the system where it will foul heat exchangers. So this oil separator is trying to strip out droplets of oil that are discharged with the ammonia vapor after the compression process occurs. They're all open drive, so the electric motor that's driving the compressor sits outside of the refrigerant stream. Here's what the oil separator looks like on the inside. Discharge gas comes out of the compressor, high pressure, high temperature with droplets of oil, and that oil is just separated out in a first stage of separation just by slowing the gas down to let the large droplets fall out by gravity. And then they're forced through, the gas is forced through a second stage of separation that uses a series of coalescing elements to remove the small droplets of oil, and hopefully the discharge gas that goes up to the condensers will be largely dry. In addition to screw compressors, smaller systems may use piston type or reciprocating compressors. The photo on the left shows a reciprocating compressor, and really simple, they're typically used in small systems. The condensers, that's our means of heat rejection, and by and large, these systems use what are called evaporative condensers. The evaporative condenser has a serpentine coil heat exchanger that carries the refrigerant inside of a cabinet where we spray water over the outside surface of that heat exchanger. A portion of that water evaporates and carries heat away from the refrigerant, and we get a highly effective process where we have condensation occurring inside the tubes of this heat exchanger, that's the refrigerant, and we have some evaporation occurring on the outside surface of that heat exchanger. So we get very effective heat rejection. And again, by the time the refrigerant makes its way through the serpentine coils of this heat exchanger, it will get fully liquefied and still remain at a high pressure. So we have condensed liquid refrigerant that comes out and is drained into the high pressure receiver. The air is moved through this heat exchanger. Here we see two condensers up on the roof. These have fans that blow air from the outside up through that cabinet, discharging out the top. You'll also see some configurations that have fans sitting at the top, and they'll draw ambient air through this cabinet, and the air runs counterflow to the water that's being sprayed over the outside surface of that heat exchanger to enhance the heat rejection capability. So here's a couple of other condensers. You'll see two lines here up on the top that are blue. Those are the gas inlet connections to the condensers. The lower ones are the condensed liquid, right, on either side. The green line is water line that goes to the spray distribution system that wets this component. This is what this heat exchanger looks like that sits inside of that cabinet. There's a large gas connection that takes the refrigerant in, and a header distributes it to a series of parallel tubes that are arranged in a serpentine coil fashion. And then there's another header at the bottom that will collect the condensed liquid and send that off to the high pressure receiver, which is simply a large vessel that can be either oriented vertically and located in a machinery room space indoors, or it can be configured horizontally. In this case, the high pressure receiver is located outdoors. The plant will use some means of being able to give the operators an indication of the liquid level. In this photo on the left, that shows that by a series of bullseye sight glasses. And the photo on the right, they actually have a continuous level sensing with what's called a magnetic level indicator. So the level in this high pressure receiver will just fluctuate up and down as the demand for liquid out in the plant fluctuates. The systems also use the terminology, the lexicon in ammonia refrigeration systems is sort of interesting. They'll use a component called a king valve. The king valve is effectively a master shutoff valve that we can close and interrupt the supply of liquid out to the plant. And here's an example of king valve. So this is in the liquid line off the high pressure receiver, so that if there was some loss of mechanical integrity out in the system, that valve could be closed and mitigate a release. The evaporators, these are direct expansion evaporators. We're looking at ceiling hung units that would be conditioning a dock area. So this sits just below the ceiling. Refrigerant piping would come in from up on the roof. The photo on the right shows evaporators that are serving a freezer space, and these would be located in a penthouse that sits actually above the roof line. There's all sorts of other configurations that you'll find in these facilities depending on the express need of the process. Fin coil evaporators are used for cooling air, and it's everything from conditioning a production space or a dock area to very low temperature freezing systems for rapid freezing of food products. We'll also use what we call chillers. These are refrigerant to liquid heat exchangers that can either be configured as shell and tube or plate and frame or falling film or scrape surface. And here are a couple of photos that just show. Photo on the left is a shell and tube liquid chiller that's cooling glycol, and the one on the right is a plate type plate and frame heat exchanger, again cooling glycol, that then is sent off to provide process cooling. And then lastly, the suction trap. This is simply a vessel that will strip out any liquid that tends to come back from the loads to protect the compressors. And this has a pair of transfer drums that will function to transition or move that refrigerant from the suction trap to another part of the system where it could be reused. Its purpose in life is to protect the compressors from ingesting liquid. This is another configuration of a single stage system, but instead of having the refrigerant in a direct expansion arrangement, this is what we call a gravity flooded system. So if we look at what's happening here, I'm going to throttle high pressure liquid to a lower pressure simply across a hand expansion valve. I'm going to form a mixture of low temperature liquid and vapor. This vessel will separate out the liquid. It's going to be a low temperature liquid. It falls to the bottom, and the gas will go directly back to the compressor suction. And now I'll connect this little vessel that we call a surge drum up to an evaporator. Liquid is going to flow by gravity, fill the circuits of that evaporator, and as I apply heat, the liquid will immediately begin to boil. And because the liquid is lighter, the vapor is lighter than the liquid, the vapor flows out the top, and we will make a return connection above the liquid level in the surge drum. And what I establish is a natural circulation of liquid flowing into the evaporator, being converted to a vapor, and the vapor being vented out back to that surge drum where it goes to our compressor suction. And this natural circulation is just driven by gravity and the fact that the liquid is heavier than the vapor. The greater the heat load that I apply in this evaporator, the greater the circulation rate. And the only thing that I'll have to do from a refrigerant control standpoint is periodically provide some replenishment or makeup of that liquid. And I'm simply going to use a float that will sense the drop in liquid level and periodically energize and de-energize the solenoid valve to batch refill this surge drum. This arrangement allows us to run with much, much lower temperatures. So we could be running in a deep vacuum somewhere in the range of 32 kPa, which would be about minus 54 degrees C evaporating temperature. And I could run all the way up to 10 degrees C or higher, which would correspond to about 615 kPa for ammonia. So very flexible. And when you have processes that require really, really low temperatures, this is a technology that you'll see deployed for that purpose. Here's an example of what one of these surge drums looks like. It's feeding low temperature liquid into the bottom part of this heat exchanger, and the vapor that's produced will get vented back into this surge drum, and then that gas is taken off the top of that vessel back to the machine room where the compressors can compress it. There's our float that's going to sense the liquid level. The solenoid valve that will provide makeup high pressure liquid that's throttled across the hand expansion valve. And we have a little bit of oil that's accumulated in the tailpipe of this drop leg. And that will get periodically drained manually by plant personnel. The last configuration is what we call a liquid overfeed. Instead of having each evaporator with its own individual surge drum, I'm going to have a single larger vessel that's located in a mechanical equipment room that I'll throttle from high pressure to low pressure. I'll form that flash gas and I'll have a reservoir of low temperature liquid, but now I'll use a small centrifugal pump to push that liquid out to evaporators that have a common temperature requirement in terms of load. Those evaporators will take on that low temperature liquid, pick up heat from the space to boil off the liquid refrigerant. So I'll get some space cooling or process cooling. And what I'll have by design is a mixture of vapor that's produced by meeting load and some unboiled liquid come back out of these evaporators. I'm going to supply more than what they need so that in a single pass, I'll have liquid and vapor coming back. And I do that to try to keep all of the inside surfaces of this heat exchanger wetted with liquid refrigerant so I get good performance. And what I'll do is I'll bring that vapor back to this main vessel. And if the liquid that comes back, it hasn't changed in temperature, I will simply separate out by this vessel. The liquid falls to the bottom to get reused again, and the vapor goes back to my compressor suction where it can get compressed and condensed. And so the high pressure side of this system is virtually the same in all three of those configurations. And so we call this a pumped liquid overfeed. Still has the same operating temperature capability as the gravity flooded recirculation, running down as low as maybe minus 54 degrees C or 32 kPa, which is a deep vacuum for ammonia, and maybe as high as plus 10 degrees C or 615 kPa corresponding pressure. So those are the three most common ways that we configure the evaporators in these industrial systems to meet a wide range of load capability. And here's a couple of photos of what this recirculator looks like. So a large vertical vessel in this case, and there's two small liquid refrigerant pumps that will be responsible for circulating liquid out to evaporators like this heat exchanger that's sitting in a penthouse and providing cooling for a low temperature holding freezer for finished food product. So valve groups and all of the piping on these systems are typically located outdoors. They're up on a roof so that they're not going to be in the occupied space where there's industrial personnel or a space where I have products. So if I do get any sort of release of refrigerant from the valves or piping, I'm not going to put people at risk or stored product at risk. Okay, just given where we're at on time, I'm not going to spend really much talking about two-stage compression, but what I will say is when we have needs of lower and lower refrigerant temperatures to satisfy process requirements, we'll often go into these compound systems that have really low temperature requirements. So this is showing a minus 40 degrees evaporating on the low temperature side, and I'm condensing at plus 35 degrees, so a big pressure lift that would be required if I was going to do that in a single step. And so what early practitioners realized is they could configure the compressors to run in series if I could cool off the discharge gas from this lowest stage compressor that we call a booster compressor. And so this, what we call compound or two-stage compression system, enables us to do that by maintaining fairly modest compression ratios for both the low stage compressor and the booster compressor. In this case, showing that each compressor is running at a 4.3 to 1 compression ratio, whereas if I tried to raise the pressure of this gas at the lowest operating condition in my plant all the way up to condensing, I'd have about an 18.8 to 1 compression ratio, which is pretty difficult to do. But by splitting it up into two steps, going from low pressure to medium pressure, and then from medium pressure to high pressure, I can greatly reduce the compression ratio in each stage of the process. So what's a typical system? That's what makes these really interesting. There's no typical, they're all sort of custom engineered for a purpose, and it makes it quite interesting. You see a wide range of applications, a wide range of heat exchanger technology, a wide range of how the systems are actually put together to serve unique needs that exist in a lot of these food processing facilities. So ammonia has been the mainstay of refrigerant in the cold chain in the industrial sector. It will be for the foreseeable future. I don't see it sort of slowing down at all. In fact, it's sort of picking up steam. We have to manage its hazard. It is a class B refrigerant. It's toxic, so we have to manage that. Fortunately, it's self-alarming, so people won't go into a space where ammonia is present. Trust me on that one. And when we're searching for sort of the next generation of refrigerants that have low global warming and no ozone depletion potential, there's a lot more interest beyond the industrial sphere with how ammonia might be used in other applications that are less traditional from where their comfort zone is. So with that, I will stop here and field any questions that you might have.
Thanks, Professor Doug, for nice presentation.
Yes, thank you, Professor Doug.
Hand over to you.
Okay, thank you very much. There are a few questions here. I'm going to run through some of them if we have time for all of them. First question is, what is the difference between ammonia and HCFC?
So HCFC, for example, R22, significantly different in terms of R22 being a fluorochemical refrigerant. They each have their different properties, so they have different pressure temperature relationships. Of course, R22 is an HCFC that has now been phased out for production in developed countries, and so it's actually a refrigerant that we're transitioning away from. It does have, R22 does have some ozone depletion potential. That's why it's being phased out. And it has a fairly significant global warming potential component, whereas ammonia has no ozone depletion, no global warming potential. The toxicity is different. So R22 and other HCFCs, with some exception, are considered Class A refrigerants. That is, they're less toxic. And then ammonia is a Class B refrigerant, which is a higher toxicity. Another HCFC that is a Class B refrigerant, low pressure refrigerant, is R123. And that's phase out is coming up in 2030.
Okay. Thank you very much. And then a question from Shida. How energy efficient is ammonia?
So it's among the most energy efficient from a thermodynamic standpoint. Some of the newer fluorochemical refrigerants that are being developed have good efficiency, and the fluorochemicals get a big benefit from being able to use high conductive materials like copper, where we can't use copper with ammonia, and we have to use less conductive materials. So there is a bit of a degrade comparatively in terms of efficiency from a materials perspective. But from a systems perspective and from a thermodynamic perspective, it's among the most efficient. It also has the benefit of being able to cover a very, very wide operating temperature range. Other refrigerants that we typically see in fluorochemicals are maybe have their sweet spot as a low pressure refrigerant would typically be used for higher temperature applications like chillers, and then the medium and high pressure refrigerants we would typically use for lower operating temperature systems. Ammonia has a very wide envelope that it maintains good efficiency and capability to use. So if you look at plants that have wide temperature capabilities like food process, I have processes that may require minus 40 degree refrigerant and maybe up as high as plus 10 degree refrigerant. I can do that all with a single refrigerant. Where you start looking at some of the fluorochemicals, I have to use some different refrigerants for each of those ranges of operating conditions that are required.
Okay, thank you very much. And then a question from Ramakrishna. Is it true that 1 kilogram of water can dissolve around 17 to 18 kilograms at constant temperature?
I'm assuming I think it's about right. Side. Okay, my brain isn't wired quite on kilograms, but it's about by volume, it's about an 8 to 1. So if you look at it on from a liter perspective, it's about 8.5 liter. One liter of water can dissolve about 8.3 liters of ammonia.
Okay. We'll just have to reference that back to the weight of the ammonia for the liters. Thank you. And then a question from Shivraj. Ammonia has a 0 GWP. Why is it mentioned as a low GWP?
Well, I sort of alluded to that before, and it's a bit of an artifact. I mean, I think it's classed as 0 GWP, but where does the ammonia come from? The ammonia comes from reforming natural gas, so CH4. So in the production of ammonia, what they do is they take natural gas as the feedstock, CH4, they break that molecule apart and use the hydrogen, combine that with nitrogen from the atmosphere, and they produce NH3, that's the ammonia. And the effluent stream off of that manufacturing process for the ammonia is carbon dioxide. And so, okay, I have my ammonia and I have carbon dioxide. Well, how do I assign? I mean, I would not have liberated any carbon dioxide if I didn't produce the ammonia, and if I didn't use natural gas, CH4. So, in theory, ammonia has no ozone depletion potential, but all of it goes to CO2. I mean, it's a bit of I guess, a philosophical accounting of who's assigned the carbon, right? And
yeah, so this one's more in the manufacturing process.
Yeah, it's a consequence of the manufacturing process. And you may or may not know that the single largest, what we call carbonic. So we use a lot of carbonic in industrial processes. The byproduct, or the waste stream for ammonia, is the primary supply for carbonic globally.
All right. Thank you very much. And then a question from Sridhar. What device exactly do we use to throttle the ammonia refrigerant? Is it a capillary tube or something else?
No, so the capillary tube would be typically something that would be used in very small systems, either like window units or home refrigerators. In these systems, the technology is pretty simple. In some cases, the expansion device is literally a ported, manually adjusted valve that we call a hand expansion valve. So instead of having just a flat disc like you would see in a shutoff valve, this will have a engineered port that is designed to throttle refrigerant from a high pressure to a low pressure, and that's manually adjusted. We also use thermostatic expansion valves. That's a modulating valve. And today we use other types of valves like a motorized valve that will stroke open and close to vary the amount of refrigerant that is throttling depending on the load. So there's a wide range of devices that are used. They're all types of valves. We don't use, in this case, we don't use any capillary tubes. The systems are too large for that.
All right. And then a question from Prithviraj. Which type of compressor is suited for maximizing the performance of VCS?
So, you know, the answer to that depends on, is the system going to run at part load for a substantial period of time? But what I would say is, from a technology perspective, ammonia is going to use positive displacement compressors, and they're all, for the most part, open drive. And so we have limited choices in our world. They're typically going to be either screw compressors or reciprocating compressors. Smaller systems, in terms of cooling capacity, will utilize reciprocating compressors, and they run really well at part load. Larger systems are going to use screw compressors, and they don't run so efficiently at part load. And so manufacturers today will do things like install variable speed drives on screw compressors to be able to maintain better performance at part load condition. And that's been a really helpful technology to run more efficiently at part load.
Okay. I think that also answers a few other questions on the list. Then another question, what is the power consumption compared to another DX system? So I'm assuming that's quite a vague question in terms of DX, because that's all refrigerants.
Correct, yeah. And so I think, let's put it this way, it's really hard to do a head-to-head comparison, because, you know, there's always somebody that's going to turn a dial differently depending on kind of their perspective. But in sort of trying to compare these even-handedly, and there's been a number of studies that have done this, the ammonia systems are capable of running more efficiently compared to a fluorochemical system. And so, you know, the biggest impediment on a sort of equal comparison basis, and again, a benefit that fluorochemical systems have, is the ability to use highly conductive materials in heat exchangers like copper. And that's a pretty big advantage. In ammonia systems, they're going to typically use carbon steel, stainless steel, or aluminum as heat transfer surface. And aluminum is good and to kind of close that gap. But that's a relatively new development that's not been around for, you know, 100 years. It's the older systems, and there's still a lot of carbon steel that's used, and the conductivity, of course, isn't as good as copper. So even with that, the ammonia systems are built and do run more efficiently in comparison to a number of the fluorochemical systems.
Okay. And then another question from Shivraj, the use of ammonia in comfort cooling applications. Is that something that would be considered? I think that depends on your capacity of your system and safety as well.
Correct, yeah. So larger applications, and I use the McCormick place as an example. So larger tonnage cooling, there is some interest in that, and there have been systems deployed. The issue there is you're you're always going to, if it's a comfort cooling application, you're pretty much going to have a secondary fluid. So you're going to use either chilled water or glycol for cooling. And again, that you pay for that heat exchange, right? So if it's a system that you're looking at contemplating a fluorochemical chiller or ammonia, that's an interesting comparison. But I think that's why people are looking at this and saying, hey, can I use a refrigerant that has no ODP and no GWP? The answer is yes. What I would say also is, because that's a relatively new technology application, the chillers are not as refined and highly engineered as you would see for fluorochemical systems. Will they be in the future? Well, we'll see what the market does. Is there's more interest and more take up of this technology for that application, I think the engineering will come along. But when you compare an ammonia chiller for that application from a fluorochemical chiller, the fluorochemical chillers are more highly engineered. They've been around longer in that application, and they have the benefit of that.
Right. And then a question from, if I'm pronouncing correctly, Vui-san Nani. Where do ice dams come into the system, and how great are they from an energy point of view? So I think that's in reference to the low temperatures you can achieve with ammonia plants.
Oh, so say again, what can you rephrase that?
Where do ice dams come into the system? So that seems to reference ice storage systems.
Oh, okay.
And that would link back to the low temperatures you could achieve with an ammonia plant.
Yeah, I mean, these systems can be used with ice storage as a thermal storage media for sure. I mean, they've done that routinely. So that's not a problem. And they're also used in actually commercial ice production. So if you're looking at ice plants, they're actually making ice for consumers or for use in process. A pretty straightforward application and use of this technology, really widely used in ice making.
Yeah. And then another question from Kalimula. In water systems, can we have one temperature in and out through the system, and then or the alternative of having two temperatures coming out of the system? So I would assume that's not a form of heat recovery in this case. I think they're looking for, say, -5 degrees and then +5 degrees temperature. I think that might be easier achieved on the ice side.
Yeah, so in the first example, the direct expansion, I showed you a couple of different temperatures that you could have heat exchangers on the low side operating at, which gives it great flexibility. The thing to keep in mind is when I'm running a single pressure on the low side, in that case, we were running, about -10 C, every heat exchanger that I put on that system running at a higher temperature, I'm effectively paying from an efficiency standpoint as if it was running at -10. So what designers have to do is look at balance and say, hey, if I have a lot of load at high temperature, I'm probably going to dedicate a separate suction pressure level and compressors to serve that higher operating pressure and temperature requirement. But if I only have 1 or 2 evaporators, I can't justify that added capital cost to create a separate suction level. The system's capable of doing it. The question becomes one of economics.
Yeah, so they would have to decide whether heat exchange or an additional cycle would be the option in the system. Okay, we seem to have quite a few questions. I'm not sure if we will make it through all of them. We could do a few more and then maybe do a written response at the end to the rest. A question from Bailey regarding the safety of ammonia refrigerant. I think that also goes back to why it can't be used in comfort cooling inside the building, which also answers a lot of other questions on the list.
Yeah, correct. So if you look at the standards that are used from a design perspective, we can't use direct ammonia in non-industrial environments. So, and that's because of its toxicity.
Yeah. Okay. Then we have a question from Som. Seems to be quite a technical one. Let me just read through it. How good is vapor absorption refrigeration system put in series with vapor compression using ammonia at discharge in reciprocating and ammonia and water as vapor absorption system? Have you seen any application of this nature?
Well, there's obviously aqua ammonia absorption systems, and those are capable of running at low temperatures, in contrast to something like a lithium bromide water absorption chiller that is limited only to high temperature application. The issue with absorption systems is one of capital costs. Or capital costs are pretty high because you need so much heat transfer surface. And so I'm not aware of anything that tries to couple those technologies together, if that's sort of what they're asking.
Okay. And there is, it seems maybe a cultural question, but I think it comes more back to safety as well. Any safety precautions if the ammonia is leaked in the working space? More specifically to Muslims, maybe in reference to their food preparation.
Yes. So just to give you a sense of thresholds here for a moment, most people can smell ammonia in the 5 part per million range. Okay, and occupationally, we could be in an environment that has 25 parts per million and work continuously, a 40-hour work week. Now, I will tell you that in these plants, there's not any employees that will stay there. They smell ammonia, they're going to be exiting the plant. When you get to high concentrations, and I'm talking about above 1,000, right, in the thousands, that's what we call rapidly fatal. You do not want to be in that environment, and most people will long since left if they have the opportunity. If I have a leak in a production facility and that ammonia contaminates product, here that product will not get used. It will be disposed of. So any open product that is in an environment that has had ammonia in the atmosphere in any significant concentration will be disposed of.
Yeah, I think some of the questions seem to lead back to when it's used in the space, such as for production of milk. But I know from my experience, it's depending on the system, as you've mentioned previously, sometimes it's better to keep it in a separate housing where even if there is a leak, it doesn't impact on your production, where you have a secondary water system, as you mentioned as well.
Yes.
And in terms of the safety, there was 1 or 2 questions regarding that. And I believe water sprinklers is your typical answer to the absorption of the ammonia.
Correct.
When you do have a leak.
Yeah, and the only caveat there is you never want to spray water on a pool of liquid ammonia. So it's very good to decontaminate body. So eye wash and safety shower if you get any exposure on your skin. And it's very effective at knocking down vapor and absorbing ammonia vapor. But we don't really want to spray water on liquid ammonia because the heat from the water will cause a more rapid evaporation of the liquid.
Okay. Let's see, there's still quite a lot of questions. I'm not sure how we are doing for time. Just have a look here quick. Shalindra, I'm not sure if you can advise on how much time we have left.
I think we have covered a lot of questions.
Okay. I think we can I think we can download the rest of the questions, and if there's anything that we didn't cover now in the chat, we'll just do a written response, if that's all right.
Yep, that's fine.
Okay, great. Then thank you very much, Professor Douglas, for your time, and so for the Rajasthan chapter for helping to host this and collaborating with the South African chapter. We definitely appreciate it, and we definitely appreciate your time, Professor Douglas, and your insight. this is definitely something that might become more common going forward, and something that a lot of people are not aware of due to the fact that it's not used outside of many industrial applications at the moment. So I think the participants learned quite a lot, and that this information will be used going forward productively for all of us. Yes, thank you again for your time, and we look forward to chatting to you again in future.
Thanks for having me, and enjoy the rest of your World Refrigeration Day.
Thank you.
Thanks, Professor Doyle. Yep. Thanks, Mr. Declan.
It's a pleasure. I think we can close out and say good day to you, Professor Douglas. I hope you enjoy the rest of your day and your weekend, and good afternoon and good evening to all the participants on the group. Stay safe during these tough times, and we hope to see you all again soon.